Hey folks, we're going to do a quick LC circuit example. So let's say we have a simple LC circuit. So we have a capacitor and we have our switch and we have our inductor. That's L, okay, and you got like that. And let's say your circuit starts with the capacitor fully charged to a voltage V naught, okay. So you will note we have exactly three letters on the page, right? L, C, and V naught, okay? Here, and then let's say at t equals 0, we close the switch. I want us to determine the following in terms of those givens and fundamental constants. We're going to determine the period of oscillation of the charge, the frequency of oscillation of the charge, the maximum charge, the maximum current, the charge as a function of time, the current as a function of time, and the total energy stored in the circuit at any moment. Okay, the total energy of the circuit. All those things in terms of only these three letters. So our answers can only have those three letters in it. All right. Well, okay, so let's start off with I know that omega from the previous discussion is 1 over root LC. So I immediately know that frequency is omega over 2 pi. So if you're doing, remember omega is how many radians per second you're doing. Frequency is how many cycles per second. You just divide by 2 pi for that. So for our frequency, it's 1 over 2 pi root LC. I also know that my period is 1 over the frequency. So our period would be 2 pi root LC. Okay, so far we've gotten period and frequency off that list there. Okay, Q max. Well, that's easy. Q max is simply equal to CV naught. All right, so I've got that. So I've got that, got my frequency, I've got my period. Okay, Q is a function of time. Okay, so that's a little more exciting. So Q as a function of time would be Q max, which would be CV naught. And we're starting with the capacitor fully charged. So at time equals 0, I want my function to equal 1. So I'll use cosine. So this would be cosine of omega t. However, I can't use omega. That wasn't one of my three givens. But I do know that omega is 1 over root LC. So I can rewrite this as charge as a function of time is CV naught cosine of, I can write 1 over root LC times t, but I'll just write this way, t over root LC. Okay, so that is the charge as a function of time. As far as current as a function of time, so I got this. So current is the derivative of charge, so it's dq dt. So I'll just take the derivative of this. So I is equal to, well, the derivative of cosine is negative sign, so I'll throw a negative out front. We got CV naught times the derivative of what's inside here, which is 1 over root LC, and then it's sine of t over root LC, okay? And I'll tie that up a little bit. So I, as a function of time, is negative. I've got a c up here and a root c down there, so that becomes a root c in my numerator. And so you would have negative v naught root c over L sine of t over root LC. Okay, so that is my current as a function of time, which also leads us to I max. I max is the coefficient there, which is v naught root c over L. So that's our I max. All right, so what else did I ask you to figure out here? Okay, we got I max, we got this function of time. Oh, total energy. Okay, so energy, there's a couple ways to do this. I would look at the capacitor, okay, and we know there's three equations for energy stored in the capacitor. So let's look at the moment when all the energy is stored in the capacitor and the capacitor is fully charged. In other words, our starting condition. When we started, all the energy was stored in the capacitor. So U of a capacitor, and remembering that Q equals CV, okay, U of a capacitor is Q squared over 2C. But if I sub this in, you would get 1/2 CV squared, and then you could also say 1/2 of QV. All those are versions of the equation for energy stored in a capacitor. Well, I'll use that one. So the energy stored in the capacitor at the beginning, which is all the energy we have in our system, is 1/2 CV naught squared. And again, all of these answers, every single answer I've written, is in terms of the three things: C, V naught, and L. Okay, and fundamental constants. We got pi. Okay, so there you go. All right, so there's an example of determining different stuff about an LC circuit. Now, by the way, for a lot of these things, there's several other ways you could have approached these. This is just one example of how to approach these answers. There's probably several ways to get some of these answers, and that's fine. Okay. All right. I hope you found that video helpful, and thank you very much.